Hello and welcome. In this video, we'll talk about factoring polynomials. There are two big theorems that are tied into the process of factoring polynomials. The first one is the remainder theorem, and the second one is what we call the factor theorem. We're going to get started with the remainder theorem first. And I'm a big fan of proving theorems because it gives us a lot of certainty and confidence when we know how things are derived. We know how they've been proven to be true, and we appreciate them more because we have gone through the whole process of it, so we remember them better. So in order to better understand how the remainder theorem works, I designed this investigation. And in this investigation, what we are doing is we are performing some various divisions. I've chosen a polynomial f of x of the form f of x. And as you notice here in all these examples, f of x, or our dividend, is the same. And we're dividing f of x by various binomials, so x minus 2, x plus 2, x minus 1, x plus 1, and so on. So the whole idea behind it is that after we perform each and every division, we are going to find the remainder. And once we find the remainder, obviously we're going to list all the remainders in here. We also want to find the value of the dividend, or the numerator, or f, at b, where b, remember, is the constant that you are subtracting from x in each and every one of these divisions. So let's get started. So first, I'm going to start by identifying the value of b. In the first example, we have x minus 2, so this is in the form x minus b. So we're going to say that b equals 2. So we're dividing by x minus 2 here. The next one, we have x minus negative 2, so that means b is negative 2. And then divide by x minus 1, b is 1. And since we're here, I'm going to have to write in here f of 2, f of negative 2, f of 1. In the next division, the value of b is negative 1, so x minus negative 1. So that means we're also going to have to find f of negative 1. And then we have x minus 3, so b is 3. So we'll have to find f of 3. And then x plus 3 is x minus negative 3. We remember this from grade 10, don't we? So negative 3, so we'll have to find f of negative 3 as well. And b is 4. And we have to find f of 4. b is negative 4. So that means we have to find f of negative 4. And then b is 5. So we have to find f of 5. And then b of negative 5 here means that we are going to have to find f of negative 5. Okay, so that's what it looks like. So I'm going to start dividing very quickly because it's a process that we've been through before, and I hope that we've mastered it already. If you need more practice, I would suggest that you print out the worksheet that has been provided to you and perform all these divisions on your own, and try to work carefully, but also focus on the speed as well. So bring 1 down. Then 1 times 2. And then add 4 plus 2, 6, then 12. 1 plus 12, 13. 13 times 2, 26. Add remainder 20. Here we go. Remainder is 20. And now we're going to find f of 2, which means that we have 2 to the power of 3 plus 4 times 2 squared plus 2 minus 6. That's 8 plus 16 minus 4. And here we get that f of 2 is 20. You probably already noticed that the remainder equaled the value of the function at 2, but again, we might as well think that it might be a coincidence. You know it's not. But let's keep going. So in the next example, we have 1 down, multiplied by -2, add 2, -4, -3, +6, 0. Remainder here is 0. So let's find f of -2. So we have -2 to the power of 3 plus 4 times -2 squared plus -2 and then -6. So that's -8 plus 16 minus 8, and that's 0. So there you go. We got the same remainder as the value of the function at -2 at b. Keep going. Number 1, and then 5. 5 times 1, 5, add 6. 6, add 0. So the remainder is 0. Let's check f of 1. F of 1 is 1 cubed plus 4 times 1 squared plus 1 minus 6. So we have 1 plus 4 minus 5, and that's 0. So we've got 3 consistent examples here. And the next example, we have division by x plus 1, 1, -1, 3, -3, -2, +2, -4, and that would be the remainder. Let's check and see f of -1. So f of -1 is -1 to the power of 3 plus 4 times -1 squared plus -1 minus 6. So that's -1 plus 4 and then minus 7. So -8 plus 4, -4. So far, pretty consistent. Check the next one. We have 1, 3, 7 times 3, 21. Add 22. Multiply by 3, 66. Add 60. Remainder, 60. F of 3 is 3 to the power of 3 plus 4 times 3 squared plus 3 minus 6. And that's 27 plus 36, and then plus 3 minus 6. And here we go, 60 again. Next, 1, -3, +1, -3, -2, +6. Oh, 0. So we're going to say the remainder is 0. Let's check f of -3. -3 is to the power of 3 plus 4 times -3 squared plus -3 minus 6. So that's -27 plus 36 minus 9. That's 0. So as you see here, the pattern is pretty consistent. And you notice that the value of the remainder when a polynomial is divided by a binomial of the form x minus b equals the value of the polynomial at b. And this is what basically the remainder theorem is about. We can continue on with the rest of the examples. I think we have exhausted all the factors because we kind of got them in here. We'll talk about them later. You can continue the rest of the divisions on your own, and you will notice the same pattern continues consistently. So I think we're ready now to draw our conclusions. We're going to say that the remainder in the division f of x over x minus b is the value of the function at b. Now the value of f of b when x minus b is a factor, and that's something else we need to actually observe one more time. So notice that in 3 different cases we got a remainder of 0. And I want to bring your attention to one very simple division, the division of number 6 by number 2. If 6 is divided by 2, the answer is 3, and we say that 6 divides into 2 evenly, meaning that there is no remainder. So if you were to write number 6 in terms of numbers 2 and 3, which are the divisor and the quotient, we can say that 6 is 2 times 3. In other words, we can say that numbers 2 and 3 are factors of 6. Okay? And of 6. If we were to divide, though, say, for example, number 7 by 2, the answer will be 3, but then some more, 3.5. So in this case, we say that 7 doesn't divide evenly into 2. So, and that's why we have a remainder. And we're going to say that 3 is not a factor of 7. So we're going to say, in other words, that if the remainder from the division, right, is from the division by a binomial of the form x minus b is 0, that means that that binomial must be a factor of the polynomial. So, in other words, we're going to say that x plus 2, x plus 2, x minus 1, and x plus 3 are factors of the polynomial x cubed plus 4x squared plus x minus 6. So the value of f of b when x minus b is a factor is 0. When x minus b is a factor of f of x, then what are the values of b? So I want us to pause for a second and think a little bit harder about this. Notice that the factors are x plus 2, x minus 1, and x plus 3. Notice that the values of b here are negative 2, and then positive 1, and negative 3. So negative 2, positive 1, and negative 3 are actually all factors of negative 6. And we're going to say that, which is the constant term in f of x, we're going to say that the values of b are factors of the constant term of f of x, which is our dividend. So that leads us to thinking that, oh, if I want to find the factors of f of x, then I must explore all the possible factors of the constant term. So to find all the factors of f of x, we must inspect all the factors of the constant term and check and see if those if the factors of the constant term will give me a remainder of 0. Okay, so we're going to say that when f of x is divided by x minus b, we're going to get a quotient, q of x. And obviously, we're going to get a remainder sometimes, Rx, always divided by x minus b, which is the division statement. Now, because we just discovered that the remainder equals the value of the function, or the dividend, at b, we may as well rewrite it as q of x plus f of b divided by x minus b. Okay, so we are sort of altering the division statement a little bit. Now, don't worry about memorizing this. The only thing you have to learn for now, or remember for now, is the fact that the value of the remainder when f of x is divided by x minus b equals the value of the function at b. So the only thing we need to focus on is that this here equals the same or means the same thing as this. So this is what the remainder theorem is about. The remainder theorem states that when f of x is divided by a binomial of the form x minus b, the remainder equals the value of the binomial of the dividend at b, of the dividend at b. And all these words can very easily be written for short in a condensed form as Rx equals f of b. Okay? Now, the remainder theorem can be further extended to include divisors in which the coefficient of x is not 1, such as when the divisor is in the form ax minus b. So, in this case, we're going to say that function f of x, if divided by ax minus b, will give some quotient qx and some remainder, right, rx over ax minus b, obviously here. Okay, so this is one form of writing the division statement. Or we can as well say that f of x equals ax minus b times qx plus rx. Okay, so that is simply found by multiplying by ax minus b every term in here. Now, the value of the remainder would be equal to the value of f at b over a in this case. Okay, and we're going to write Rx equals f at b over a. So now our remainder theorem is more complete. We're going to say that when polynomial, a polynomial f of x is divided by x minus b, remainder is f of b. But when it's divided by ax minus b, the remainder is f of at b over a. Now the first one is called the integral theorem, and the second one is called the rational theorem. And they kind of sound confusing and too fancy, but think of it this way. B has to be an integer. That's why it's given the name the integral theorem. It's not the integrals that you do in calculus, okay? So it's just a way to describe an integer, so the adjective form of it. And the second one is called the rational form of the theorem. It's the same theorem that we are talking about. So in order to determine the factors of polynomial expression when divided by ax minus b, now we have to look for two things, for the value of b and the value of a. And this is when we get into the factor theorem, which I want to separate it for the moment being. So I want to practice a couple of questions with the remainder theorem for now, and I want to have another lesson on factor theorem on day. So if you want to find the remainder when we are dividing a polynomial by this given binomial, we don't have to go through the whole process. We can find the remainder very easily by simply finding the value of the function at the value of b here. Since we have x plus 7 as our divisor, we're going to say that the value of b here is negative 7. So the remainder would be equal to f of negative 7. And f of negative 7 will be negative 7 to the power of 3 plus 7 times negative 7 squared plus 2 times negative 7 and then minus 5. And I'm going to use a calculator for this. X cubed plus 7x squared plus 2x minus 5. Okay, I hope I remember this. So I have this calculator I've uploaded actually. It's taking time. Thank you very much. And it was free actually to upload. There are some annoying advertisements obviously, but it's very similar to the TI calculators we use in school. So we have negative 7 to the power of 3, we said. And then, what did we say? We had 7x squared, so 7 times, okay, that's not what we meant. Okay, so negative 7 to the power 3 again. And then plus 2 times negative 7 squared. And then I think it was plus 2 times negative 7, was it? We're going to check at the end. And then minus 5. Let me double check. 7 times negative 7 squared. 2 times negative 7 minus 5. Okay. So then we have a 7 here. And enter. And we get negative 19 here. So we're going to say that the remainder equals negative 19. That's the answer. It's a very simple, straightforward question, usually worth 1 mark or maximum 2 on a test or evaluation. So in the next example, we have a division of 6x cubed minus 8x squared plus 3x minus 15 by 2x plus 1. Again, we're going to say the remainder, based on the remainder theorem, the rational form of it, would equal the value of the function at negative 1 over 2. Remember that the value of b over a is found by simply making 2x plus 1 equal to 0. So x equals negative 1/2. So that is the fraction we need to insert into the function. So here we go, 6. Negative 1 over 2 power 3 minus 8, negative 1 over 2 power 2 plus 3, negative 1 over 2, and then minus 15. Okay, and just for the fun of it, we're gonna do this mentally. Okay, so we have 6 negative 1 over 8 minus 8 times 1/4, and then minus 3 over 2, and then minus 15. So this will reduce to become negative 3 over 4. And this will become negative 8 over 4 negative 2, negative 3 over 2, and then minus 15. And here we go again. We have negative 17 there, negative 3/4, minus 6/4, and then minus 17. So negative 9/4 plus 17. Oh, goodness, that was fun. And we multiply by 4 here. And we get negative 9 plus 728, 68 over 4 and 59 over 4. That's the answer. Okay, you can use a calculator obviously, and you are not required to show all the steps to evaluating an expression like this, because we'll be busy with more fancy stuff obviously. And but it's every now and then try to practice doing things in your head, because we tend to lose that kind of skill as the time goes by and technology goes higher and higher. And this was the lesson for today. So just to sum it up, to summarize everything, we went over the remainder theorem, which will lead us to understanding how to factor polynomials. And we learned that the value of the remainder when we divide a polynomial f of x by a binomial of the form x minus b equals the value of the polynomial at b. And when you divide by ax minus b, the value of the remainder will be the value of the function at b over a. And if you mastered and understood this, I will be very happy. That's it for today, and I hope that you enjoyed the lesson. Bye for